Hello everyone, this is Erfan from Columbia University Civil Engineering and Engineering Mechanics Department. Currently, I am a PhD candidate. When you are seeing this video, hopefully I already became Dr. Mardan as my defense has been scheduled at 20th of June. Today I'm going to present a part of my PhD work, especially focus on how anionic biopolymers influence the rheology and 3D printability of the earthen material. I was planning to present like both anionic and non-ionic biopolymers on this meeting. Unfortunately, the reviewing process for non-ionic polymer paper become extremely slow. We're not sure how long it may takes in the future, so I may present those results in the future conference. So the title for my today's presentation is Facilitating Earthen Construction through Bio-Based Materials and Additive Manufacturing Technologies. I believe Bex has already introduced enough background information for the system we are working on, so I will just give a short and quick introduction here. Current construction industry is responsible for 30% of global carbon emission and 40% of global energy use. Among them, only the manufacturing of cement is contributing around 5 to 10% of global carbon emission. For mitigating these negative environmental impact, earthen material has emerged as a potential solution due to its environmental and economical benefits. I know Earth-based materials sounds totally out of our focus today. However, Earth still shelters for more than 3 billion people around the planet, and 50% of them actually from developed country and 50% of them from developing country. And it is a vernacular building material in Europe as it is in Africa. So this material has been proven itself for a millennium, should be enhanced rather than simply replaced by industrial practices. Then the question will be why the earth-based material has been replaced by current construction material like cement and concrete. The first thing come to our mind, definitely the low mechanical property. Earth has way lower compressive strengths compared to cement-based material or concrete. And secondly, a high drying shrinkage. The strength of the earth mainly comes from the dehydration of the water, but the strength of the cement mainly comes from the hydration reaction. So in earth, the water need to evaporate, and this evaporation of the water causes lots of shrinkage of the earth, and this shrinkage eventually causes lots of cracking. In addition, we also have slow structural buildup rate because of the slow dehydration process or slow drying process of the earth-based material. In this work, we try to use biopolymers and additive manufacturing technology to solve these three challenges. First, bio-based material like biopolymers can be used as a binder, which can increase the compressive strength of the material. I believe Bax's work already showed this very well. And in addition, additive manufacturing technology, although it cannot directly increase the compressive strength, but with the architectural design of the material pathway, we can increase the toughness of the printing structure. Then the high drying shrinkage. How biopolymer can solve the high drying shrinkage or mitigate high drying shrinkage of the material? We can see some biopolymers like sodium alginate I'm going to introduce today, they can work as a superplasticizer. Therefore, it can enable the smooth and continuous printing of the material with high solid volume fraction, and which has less water. Eventually, it will has less drying shrinkage rate. And for structural buildup, Professor Arno Pirit's work already show how biopolymers can accelerate the structural buildup rate. And we also know additive manufacturing technology, as it creates way more surface area compared to traditional casting technology. Therefore, it will also accelerate the drying shrinkage process of the earth-based material. Historically, we have used many different construction technology and stabilizers. For example, we have used coblot, and in most recent year, we used lime and cement as a stabilizer for earth-based material. And in this work, we specifically focus on the new construction technology, digital manufacturing, and new stabilizers, biopolymers, specifically referring to the polysaccharide. For this purpose, we applied a 3M method. First, we investigated the micro level particle interaction between clay minerals and biopolymers, or biopolymers and sand, then studied how these micro level particle interaction affect meso level rheology and small scale 3D printing. Eventually, our architecture lab will help us to scale up these results in the macro level and large scale printing. As most of the water soluble polysaccharides are either anionic or non-ionic, today I'm going to introduce two anionic biopolymer and one non-ionic biopolymer to let you have an overview of biopolymer-stabilized earthen material. I will specifically introduce like what we got in anionic biopolymers, rheology, and 3D printability. For non-ionic biopolymer, unfortunately, I can't present today, but I will just like quickly show how it affect the suspension stability. But for anionic one, the sodium alginate xanthan gum, I will specifically show how this micro level particle interaction affect its rheology, and eventually how these rheology translated to large scale 3D printing. Every single system I'm introducing today specifically focus on one type of clay and one type of biopolymer. The clay we used in this research is kaolinite clay, as it is the most abundant clay in this planet. And you can see kaolinite basically is a plate-like particle, and it is particle size ranging from 1 to 16 micron. Why I'm showing this here is I want to tell you that particle we're using is a micron scale material. It's not nanoscale material. So when we consider the particle interaction between colloidals, we can ignore the Brownian interaction. And we also using the mineral binding characterization technique. I believe Bax has already covered very well on this part. So basically, we are mixing clay and a polymer, and we try to wash out all the polymer and see if clay and a polymer has a strong binding affinity to each other or not. I'm just going to quickly go through these slides to show which polymers is binding and which polymers is not binding, as Bax already explained it very well. So we know the anionic polymer, the negatively charged polymer like a sodium alginate and xanthan gum, they're not binding. It's pretty easy to understand because clay is also negatively charged, and these polymer also negatively charged. They have strong electrostatic repulsion force between this polymers and clay, and very strong binding affinity between clay and a polymer been found on locust bean gum because it is non-ionic and also pretty hydrophobic. So it will have very strong hydrophobic interaction between clay and a polymer. Eventually, the locust bean gum bind to clay, xanthan and sodium alginate does not bind to clay. And we have these two type of polymers, right? We have the polymer which binds to clay, which is non-ionic biopolymer, which has another polymer which does not bind to clay, which is anionic biopolymers. So let's see how this anionic biopolymer or non-binding biopolymer affect the suspension stability. You know, clay naturally flocculate and settle because of, van der Waals forces, hydrophobic interaction between clay particles. So if you like put them in a tube for 1 hour, it will show a very strong the settling behavior. But if you add like very small amount of biopolymer, this is the sodium alginate, you can see we added like 0.06%, 0.12%, 0.6%. So basically like 0.12% is enough to get pretty much stable suspension. And these two suspension has very different flocculation or settling behavior. On the other hand, these binding polymer or non-ionic locus beam gum can accelerate the flocculation process. We can see from the video, compared to the pure colonite control, the locus beam gum addition significantly accelerate the flocculation process. This is because you can imagine if a polymer bind to one clay particle, which also can bind to another clay particle, this kind of like bridging effect can accelerate the flocculation of the clay. Eventually, it will accelerate the settling behavior. Before further analysis, we could quickly go through all different kinds of particle interaction in suspension. The main particle interaction force in suspension could be divided into three categories. We have Brownian interactions, colloidal interactions, and viscous interactions. For Brownian interaction, it indicates the Brownian motion of the particle, which caused by the random bombardment of the solvent molecule to the suspended particle. And for colloidal interaction, which include van der Waals force, electrostatic interaction, steric interaction, and depletion interaction, eventually we have the viscous interaction, which also called hydrodynamic interaction. I believe not everyone is a rheologist, so I'm going to quickly introduce two concepts: what is yield stress and what is storage modulus, which will help you to understand the rest of the result. So firstly, the yield stress. Yield stress represents the minimum stress required to initiate flow in a material. Usually we use yield stress to like calculate the buildability, how high you can build with the 3D printer for the fresh state material. And secondly, we have storage modulus. So basically, we are working on a viscoelastic material, and viscoelastic material means like it has like some elastic behavior and it has some viscous behavior. And storage modulus and loss modulus specifically quantify it is elastic portion and the viscous portion. And storage modulus basically quantify the material's ability to store elastic energy during the deformation. And yeah, I just quickly Google it and find this very interesting figure. This red man drop a ball and ball bounce back a little bit. And this bouncing back portion is definitely caused by the elastic energy stored in this system, and which is storage modulus. And we also have some energy lost, and which is caused by the loss modulus. Let's see how these anionic biopolymers, the negatively charged non-binding biopolymers, affect the clay-based systems rheology. We're discussing the yield stress and storage modulus. From left to right, we are simply increasing the polymer concentration, and the first group, K60W50, is just pure clay. And K means kaolin, W means water, and 60-50 means clay to water ratio. Okay, and we can see both of them, like storage modulus and yield stress, show two trend. If you add very small amount of polymer, it immediately reduce yield stress more than like 2 orders of magnitude. Same for the storage modulus, right? And then if you keep increasing the polymer concentration, it eventually increases the modulus, increase the yield stress again. So let's see what is happening in each stage. When you only have clay in the system, clay naturally flocculate because of the van der Waals force and hydrophobic interaction, which creates some kinds of microstructure, right? And if you add very small amount of anionic polymer, as both this anionic polymer, this is sodium alginate here, both sodium alginate and kaolinite particle has negatively charged, so which will have electrostatic repulsion force between each other, which will prevent the flocculation of the clay particle. But if you keep increasing the polymer concentration, eventually the polymers started to overlap with each other to create three-dimensional polymer network, which eventually increase the yield stress and storage modulus. Now we know how these anionic polymer affect the suspension rheology, and let's see how these rheology translated to the printability of the material. The goal of studying rheology of clay-based system is that it could help us to understand the printing process. The printability of the clay is divided into three categories. This is what we call too flowable. If material started to yield, cannot hold its shape, we call this too flowable. If material can continuously extrude from the nozzle and can hold its shape, does not show any yielding behavior, we call it as printable. Eventually, like if you have like a lot of solid content, the material started to show the shark skin, we call it as unprintable. Let's see how different clay to water ratio and sodium alginate addition affect the printing status of our material. First row here is pure kaolinite. All of them is like pure kaolinite mixture. And second one is kaolinite plus 2.4% sodium alginate. From left to right, we just simply increasing the solid volume fraction or reducing the water content. Basically, when you have too much water, your material become too flowable. It cannot hold its shape. It gonna yield. And then at a specific clay to water ratio, your material become nicely printable, right? Eventually, if you like keep reducing the water content, your material become unprintable and cannot like continuously extrude from the nozzle. However, when we add 2% sodium alginate, what's going to happen is we already seen in the previous slides, it will reduce the storage modulus, reduce the yield stress, and which is very obvious from first few figures here. So it will immediately destroy its buildability. But what is really interesting here is which will push this printability window to higher solid volume fraction. Basically, sodium alginate helping to like smoothly and continuously extrude off the material with higher solid volume fraction, which eventually result in like high compressive strengths, also low drying shrinkage because you have less water in these printable mixtures. Let's put all of these results in one figure. For this figure, I used the Xanthium gum, which is work pretty same as sodium alginate. Both of them is anionic biopolymer and they're non-binding. Okay, so at the beginning, when we only have clay in the system, clay naturally flocculate and create some kind of microstructure, which has like some degree of yield stress, right? It's not the perfect material to print, but you still see some degree of buildability. Then you try to add some anionic biopolymer that's not binding to clay. Because both anionic biopolymer and the clay is negatively charged, they're going to have very strong electrostatic repulsion force, which will prevent the clay's flocculation. So at very small concentration, which will disperse the clay particle. So you see the buildability here, and it will gradually decrease. Now you see yield stress here, yield stress gradually decrease too, right? But at some point, if you keep increasing the polymer concentration, the polymers started to like overlap with each other, right? And then if you keep increasing the polymer concentration, they gotta overlap again. Then it will create this kind of three-dimensional polymer network, which will gradually increase the yield stress, increase the storage modulus, increase the viscosity. Then if you print these material, your buildability is starting to increase again. Gradually, if you keep increasing at the end, you have this kind of material, which is pretty nicely printable. Eventually, you can use this anionic polymer as a stiffener or as a superplasticizer, depending on the concentration. So if you want to use that as a superplasticizer, you probably want to just use a very small concentration. And if you want to use that as stiffener, you can use within the overlapping concentration. In conclusion, all this anionic biopolymer we studied here, including like xanthium gum, sodium alginate, we also like did some experiment on like gum arabic. All of them is like non-binding polymer where they don't have very strong binding affinity to the clay. And their rheology shows two distinctive trends. First, if you add like very small amount of polymer, it will disperse the clay particle and reduce the yield stress, reduce the viscosity, reduce the storage modulus. And if you keep increasing the polymer concentration, polymers started to overlap with each other to create three-dimensional polymer network, which eventually increase the yield stress, viscosity, storage modulus, and the buildability of your material. And With these polymer, you can enable the continuous and smooth printing of the material with high salt volume fraction, which eventually increasing the compressive strength and reduce the drying shrinkage of the material. And today's presentation comes from these two papers published in CCR, one of them about sodium alginate stabilized earth, one of them is enzyme gum stabilized earth. If you're interested, you can read more details from these two papers. Eventually, I want to acknowledge all my collaborators from Columbia University, also in University of Colorado Boulder, and acknowledge National Science Foundation for financial support, Columbia University, Carleton Lab for technical support. Thanks for your listening.